Hello everyone. Uh, Today we are going to start quantum mechanics. For that, we are just reviewing the essentials of classical mechanics, and then we are asking the question why we need quantum mechanics. So we are starting with classical mechanics. Classical. So what is classical mechanics? Mechanics is study of motion, right? So what is motion? Motion is roughly the change of position of a particle with respect to time. So that is motion. Then what do we mean by study? So what is the question we are asking when we study the motion? So we are interested in how a particle moves. We are interested in describing the motion of a particle. Uh, in a mathematical way, it is uh, it means that if we know the initial condition of a particle that is moving or starting to move, then can we predict final uh, position or the state of the system. So this is the important question we are asking when we study motion. So so we have the definition of motion, and we have the important question when we study motion. Okay, so how we are going to answer that question? So in order to answer this question or study motion, we need to make this question and the definition of motion more precise, or make it a mathematical question. Then we will be able to answer it more precisely or accurately and in a simple and general way. So the first thing we should be doing is make make everything mathematical. So the first thing when we study anything in physics, uh, we need a representation of that thing mathematically. Representation mathematically. So how we are uh, represent motion mathematically. So usually what we are doing is we draw a coordinate system. This the concept of coordinate system you already studied in the mathematical physics. X, Y, Z, and a point in this coordinate system represent position position of the particle. Okay. As time progresses, this point changes, that is position changes, and we will get a curve, some kind of curve. So this curve represent the trajectory of the particle. This curve represent trajectory. So this is how we represent it geometrically. So also we can represent this motion algebraically using a function. So this is the trajectory of the particle, which means this curve says how the position of particle changes with time. So if we can represent that curve as a function, gives the trajectory of the particle. Also, another way to represent a point is, as you studied in mathematical physics, is by a vector. So each point is a vector starting from origin to that point. So each point in this curve is a vector, and we can consider this function we can consider as a vector function. Okay, so now we represented this position or position change mathematically, and then we will ask the question, if we know the initial configuration or initial position of the particle, can we predict the final or later position of the particle? So this is the question we are going to answer in classical mechanics. Okay, uh, but later we realized that this change of position with respect to time is not as important as we initially assumed, but the more important quantity is the second derivative of position with respect to time. That is uh, change of velocity with respect to time. Okay. This will realize that this in inertial coordinate in inertial frames, uh, a particle moving with uniform velocity is equivalent to particle at rest. So, so in order to accommodate that also, uh, this dv by dt, that is the change of velocity with respect to time, is an important quantity, not the uh, change of position with respect to time. So in order to accommodate that, what we have done is that this mathematical representation, which it is known as the configuration space is one way to represent the motion, but a better way to represent motion is uh, x comma p, which is known as the phase space. So one point in this phase space, this coordinate gives the position, and this coordinate gives the momentum of the particle. So in this case, it gives the configuration of the particle, or the initial um, initial condition of the particle. It is actually configuration of the particle. Here it gives the state of the particle. So there is a difference between configuration of an object and state of an object. Uh, we can predict the future trajectory of a particle only if we know the initial state. That is, we should be able to know position and momentum. Then only we can predict the final state. We cannot predict the trajectory of or a final state of a particle only by knowing the position. So in this case, this point gives only the position of the particle, but that is not sufficient to calculate the trajectory of a particle or a final state of a particle at a later time. So we need a point in phase space. Okay, so this gives the initial condition. Point, one point in this phase space gives the initial condition. So now we represent the motion in a mathematical space. Then that gives initial condition. Initial condition means the initial state. Initial state. And there is a difference between configuration and state that we should remember. Then the second thing is that uh, now we know the initial state, then we we must be able to predict the final configuration or final state, or or the trajectory of the particle. For that, we need some laws or postulates which we know, um, Newton's law. So Newton's law, uh, Newton's second law says that the rate of change of momentum dp by dt is equal to the force. Okay, which means this momentum is m into v. This is actually d by dt of d square by dt square of m into r. So this is actually a second order differential equation. That's why we need position and velocity. So in order to solve a second order differential equation, we need two conditions, two initial condition, which is r r of t equal to 0, which is the position at time t equal to 0, and r dot time t equal to 0, which is the velocity at time equal to 0. So this is why we need position and velocity, or position or momentum, position and momentum. So that's why the representation in phase space is needed, because the law describes the motion or law predicts the motion is a second order differential equation. Okay, and there are equivalent way of describing the motion. That is, there are equivalent way to represent this thing mathematically, this law mathematically. One is Newton's law. Then you may have already studied this Lagrange's equation. Then Hamilton's equation. These all are equivalent way of representing one fundamental thing, how a particle moves, or how the state of a particle changes. So these are the essential thing we need when we study the motion. Okay, so what are those things? We need the state of the system. State of the system. System can be a particle or a collection of particles. Okay, then we need uh, laws. So these are the two things we need to study motion. Okay, so then one more thing is that the classical mechanics is deterministic. Deterministic, which means that if we know the initial state, of a particle, we can deterministically predict the final state of the particle. So if the initial state is given, we can exactly or deterministically calculate the final state. So that is why we say that classical mechanics is deterministic. Okay, so this is the summary of classical mechanics. Okay, then why we need quantum mechanics? So what is the use of quantum mechanics? The problem arises when uh, when we go to extreme limits. So here we assume that assumed many things intrinsically. So motion is roughly defined as the change of position with respect to time. So there is position and time, or space and time. In classical mechanics, we intrinsically make assumptions about space and time. So we assume that space is homogeneous, time is homogeneous, space is absolute, and time is absolute. These kind of assumption assumptions we make intrinsically when we study classical mechanics. But these intrinsic assumptions uh, will not be true when we go beyond some range of quantities. If we uh, if we study the particles which are very large, which has huge mass, then this classical mechanics may not be sufficient. Then we need general relativity. If the velocity of the particle, the speed of the particle is very large, then this Newton's law uh, is not valid. Then we need special relativity. And if the size of the particle is very small, then that particle behaves differently. Uh, so we cannot use classical mechanics there. In that case, we need quantum mechanics. And if the number of particle is very large, we already said that the classical mechanics is deterministic. That is, if we know the initial state, we can predict the final state. But if the number of particles are too huge, that is, for an example, number of particles in a room, it will be order of 10 to the power 23, order of Avogadro number. So we need to solve this 10 to the power 23 equation of motion to uh, predict the behavior of whole gas inside a room. But that is an impossible task. So we need some other approach. So that is statistical mechanics. So even though classical mechanics is useful in some range of mass, speed, and size, and number of particles, if we go beyond that size or go beyond that range, this classical mechanics may not be as useful as it is. So when we go beyond some range of length, time, or mass, or speed, or number of particles, we need some more general theories, more general extensions of classical mechanics. Okay, so that is why we need some other um, study, other perspective of looking at things other than classical mechanics. Okay.